Hello everyone, welcome back. Today we're talking about equilibrium carrier statistics in semiconductors. We left off last time talking about density of states, which is a derivation that we found for the number of available states per unit area, per unit volume, per unit energy in a semiconductor. And this is what we derived last week for density of states in the conduction band and density of states in the valence band. We started this derivation based off of the standard energy momentum plot that's plotted using the time-independent Schrodinger equation. We assumed this would be the conduction band, this would be the valence band, or in terms of the energy eigenvalues, E sub n and E sub n plus 1. But today we're going to talk about equilibrium carrier statistics, but we're going to start out by talking about effective mass before we get into that. We're going to try and do a quick discussion on effective mass and then go right into equilibrium carrier statistics. And you know, we use this to analyze density of states, this assumption, this graph right here, but in real life, experimentally, we find that the energy momentum plots of silicon and germanium, gallium arsenide, indium phosphide, a lot of the other compound semiconductors used in microelectronics don't look anything at all like this, you know. And I'm going to use silicon, for example, because that's you know, the most commonly used semiconductor. We have something that looks like this, you know. Here's a center called this. This is K, and let me just move this down a little bit here. And we have multiple bands, actually. Something like this. And something like this. So this is a more realistic picture of, not drawn to scale. There's other bands above here and below here, but this is a more realistic portrayal of the energy momentum plots of silicon crystal. And I'll say this is, you know, negative pi over A, and this here is about pi over A. And you notice here what's different is the conduction band minimum and the valence band maximum are not lined up with each other. This is not a direct, silicon is not a direct band gap semiconductor, which means in order for carriers to, in order to create electron hole pairs by like thermal generation, it needs to go through this change in momentum here, delta K, right? And our band gap is here. So a couple things you'll notice. We have multiple bands. Effective mass is defined by this relation right here. M star is equal to h bar squared d squared E over dk squared, inverse of that, right? So that's how we define effective mass in a semiconductor. You notice here we have, you know, h bar, that's your Planck's constant. You know, it doesn't have a big effect on, you know, how this would change. But we have this right here, d squared E over dk squared is the curvature of the curve. You know, that's, you know, how sharp is the curve. Has to do with how large this number is here. But it's the inverse of this, you know. So we can say that the effective mass is proportional to the inverse of the curvature. And another way to look at that, you know, that's always helped me that you don't hear in semiconductor books, it's easier for me to understand, is the effective mass is proportional to the radius of curvature. So if we have a large radius of curvature, we have a large effective mass, you know. If we have a small radius of curvature, small effective mass. What does that mean? You know, if we have a small effective mass, we have a smaller density of states. You know, radius of curvature. Use a different color to make it very. You know, to this, if we're considering the bottom of the conduction band, which is where most of this stuff is happening, that's our radius of curvature. So for this top band, we have a large radius of curvature. for this band under here, small radius of curvature. So what we call this band the heavy hole band, and we call this band the light hole band. Large radius of curvature, large effective mass, heavier effective mass. Small radius of curvature, or large curvature, has light effective mass. We call this the split-off band, which for general carrier statistics, it doesn't have a whole lot of effect on transport in the semiconductor. You know, we're going to find that actually the heavy hole band is actually the dominant term in this for the energy momentum plot. So, and also another thing about silicon, when you look at it in terms of EK, is that it has 6 different conduction bands. Right, look at it. Just like this. And inside the unit cell, and so for each one of these conduction bands, we have a transverse effective mass. Effective mass is a tensor, actually. We're going to assume it to just be a constant in this case, but it is a tensor, and you can go through some longer derivations to really get a better understanding. And I'm just going to kind of show a little bit. We have 2 longitudinal effective mass and a transverse effective mass for each conduction band. So there's actually 6 conduction bands. So that's 6 different conduction bands that you could have available states for electrons. So so if you think about it, like if I have an electron here at the bottom of the conduction band, it's going to have a smaller effective mass because it has a smaller radius of curvature, as opposed to if the electron was right here, higher up in the conduction band, which of course this has a very very large radius of curvature, so a very large effective mass. But in semiconductors, we always experimentally we see that most of the time when we excite new carriers, new electron hole pairs are created, they accumulate within the small area, either at the bottom of the conduction, at the top of the valence band, which is where our holes are, or for the electrons, just at the very bottom of the conduction band. And it's about energy kT above the conduction band minimum is where most of our carriers are going to be, all into here, So that's effective mass. So for a hole, we have M star P light hole and M star P heavy hole. And in this case, we're really only going to be considering the heavy hole effective mass, because that's the one that's going to be the dominant term, and that's going to dominate in all these derivations we're making. But I just wanted to show that before we got into the equilibrium carrier statistics. So use that for now. So all of these equations we're going to be using, the variable that's going to be changing is energy E. Energy E is the energy that some state is in the work that we're analyzing. And the first term we're gonna talk about, the first relation we're going to talk about that we didn't talk about last week is the Fermi function, which is f of E. And that is equal to 1 over 1 plus E to the E minus EF over KT. Right? The Fermi function tells the probability of a given state, if a given state in conduction band or valence band is occupied by a carrier. Right? So it's a function of energy, of course, and EF is the Fermi level. And for intrinsic semiconductor, which is what we're only going to be talking about today, intrinsic semiconductor, which means no doping, pure, just a pure semiconductor, EF is a constant. And what we're going to kind of do today is go through some derivations to find out what that value is. And actually, in an intrinsic semiconductor, we call EF, which is the Fermi energy, is equal to EI for intrinsic. And yeah, so if we the Fermi function, if you think about it, it's if we added some kind of dopant like boron or phosphorus or something like that, whether or not that dopant became ionized has to do with this equation right here. And if we look at this, what happens if E is right at EF, right at the intrinsic Fermi level? Well, this is 0, right? And which means this term is just 1. And then our Fermi function is 1/2. So it's 50%. 50% is a 50% chance that the state is occupied by some carrier, an electron, if it's in the conduction band. So I'm going to rewrite this equation over here so we can have it available. That's our Fermi function, the probability that a state is occupied by a carrier. That carrier could be an electron. Well, it can only be an electron, actually, yeah. Because if we wanted to know the probability of if a hole was occupying a state in the valence band, it would just be 1 minus F of E. So 1 minus F of E is the probability that a state is not occupied, right? Because F of E can only be between 0 and 1, right? So if it's if there's a 50% chance that it's occupied, then there's a 50% chance that it's empty. 1 minus 0.5 equals 0.5. Okay. That didn't even need to be said. But so how do we know the total number of carriers, of electrons or holes in a semiconductor? How do we figure that out? Well, let's take we only know that free electrons exist in the conduction band and holes exist in the valence band. So let's consider electrons in the conduction band, right? N is number of electrons per unit area, centimeter squared. So N is equal to at some energy E is equal to GC, that conduction band of E, times F of E times some change in energy E. Let's go back to what the conduction band looks like. Looks like something like this, right? There's E, here's K. Oops. Right? So if I have some DE here, what's the density of electrons in this area right here? That's what we're looking for. Actually, we're going to look for a general term for this, but we're going to start with just this right here. So that's how many electrons are that. So actually, if I want to find out how many electrons are in this entire conduction band, well then I'm just going to integrate from the conduction band minimum to infinity, right? Just assuming that it goes on forever. But before we start solving this integral, I want to show what some of this stuff looks like graphically, right? So GC of E, if this GC of E, and here's E. What does this plot look like, right, in the conduction band? It looks like this, right? Let me draw that. Remember, this is a flip of the graph that we did last time, right? Because it's proportional to the square root of E. So when we just think of this is E, and this is GC, and this is E, it goes up here and it saturates. That's what the square root of terms is like there. So we're flipping it just like that. So as we as the density in states increases, so does energy, and it actually increases exponentially there. So that's what GC is. But what does the Fermi function look like, right? Well, the Fermi function looks like this. The graph here. Fermi function looks like this. Right? This is F, and this is E. Just like that. So as we go across, at F equal to 0, make sure I wrote that right. Yeah, just like that. So, and then if this is F and GC, you know, it looks something like that, you know. And we're looking in the area of the solution area, which is this right here. So we're going to come back to this plot a little bit later on, but for now, let's look at what we got here. So GC and F of E. So let's start, you know, writing this integral out. What does this look like here? So I'm going to pull out the, you know, the MN, and we can take an effective mass to be constant in this case. It's not necessarily true, but we're going to assume that in this case, and we're going to pull out N star to the 3 over 2 times root 2 over pi squared h bar 3, integrate from E, that's a back integral sign, EC to infinity of E minus EC over 1 plus E to the E minus EF over KT dE. That is what we are. This is our total number of carriers per centimeter cubed in the conduction band, right? In the entire conduction band. This is not an easy integral to solve. We're going to make some substitutions here, you know, some use of. So we're going to say that we're going to say this. Erase some stuff here. Go back to this. We're going to say that this variable eta is equal to E. Make sure E minus EC over KT. Right? Now we're going to also make a variable at the C is equal to EF minus EC over KT. Well, this is basically a constant, right? Because we call EF a constant. It's a constant for intrinsic carrier concentration in a semiconductor. This, however, has the variable E, which is going to be changed. We're integrating with respect to E. So AD eta is equal to BE over KT. Right? And look at this right here. Right. Well, let me rewrite this so everything fits in here. Right. So we gotta make some substitutions here. So we need you know, DE to be equal to KT d eta, right? So I'm going to multiply top and bottom by KT. Right? This should be, you know, this little algebra and calculus here, nothing too bad. And here's another tricky part. E minus EC is this. So we need to, so this whole term is going to get, you know, square rooted, right? So that means we need to square root KT, square root KT, just like that over here. So here, this term here is going to be this square root term here. And this term, check here, is this guy right here. Right? That's what that corresponds to. So I'm going to rewrite this integral just like this. Take a good look at that because I'm going to erase it because I'm out of room. So going to be rewritten as root 2 m n star 3 kt 3 all square rooted over pi squared h bar 3 integral neta to the 1/2 d neta over 1 plus e neta minus neta c. Right? Because if we subtract this from this, that ends up just being EC cancels out, it's just E minus EF. Right? So that's still not really an integral you can really solve using basic calculus techniques. However, we can make some we can actually rewrite it in terms of this right here, which is we can take this whole term and rewrite it as f to the 1/2 nc is equal to 0 to infinity of eta to the 1/2 over 1 plus e to the eta minus neta c, just like that, right? And so we're going to leave it like that, and then go back up here, get rid of that. And this right here is known as the Fermi-Dirac Integral. And for an intrinsic semiconductor, or I mean, not intrinsic, for a non-degenerately doped semiconductor, this term can be simplified to root pi over 2 e to the EF minus EC over KT, just like that. That is our Fermi-Dirac integral right there. So, we can rewrite this right here. Now this assumption is only true for non-degenerately doped semiconductors. And what I mean by that, in a mathematical sense, it's about 3 kT in energy from below the conduction band edge to about 3 kT above the valence band edge. Right? So, for semiconductors like this, in terms of X, if you write the energy band diagram in terms of distance and not K anymore, it's going to look just like that, because we're just dealing with, this little area here, and this little area here, this is our valence band, this is our conduction band. If our, and I want to talk more about degeneracy in the next lecture. There's a lot more to it than what I'm saying right now, but this is just kind of a mathematical representation, so we can use the Fermi-Dirac integral, right? So this distance here is, 3 kT. And this distance here is 3 kT. So when we're in this area right here, which is basically in the band gap, we can use this assumption right here. Right? So, and that's what we're going to be doing from now on, basically. So we can actually rewrite n of E equal to this times pi over 2 e to the EF minus EC over KT, just like that, right? And furthermore, we can rewrite this whole thing as NC, which is equal to square root mn star kt, right, over, make sure I got this right here, over pi, over 2 pi h bar squared, 2 out here, to the 3 over 2. That should maybe be familiar to you. NC is referred to as the effective density of states of the conduction band in semiconductor. All right, so I'm going to rewrite this over here. Therefore, N is N of E is equal to NC e to the EF minus EC over KT. I may have made a little mistake there. Let me just double check here. I think EF is supposed to be E. No, that's correct. Okay. Right. So, this is the number of electrons per centimeter cubed in the conduction band. And this equation holds true for pretty much any non-degenerately doped semiconductor. So, only doped to a certain level. If it's doped beyond into the degenerate zone, becomes degenerate, then we have to go back to the Fermi function and use that approximation there. And with a little bit of MATLAB, and some programming, you can do that. But we can assume this for most of these problems. And similarly, I'm not going to go through the whole derivation for holes, but you can do the same thing with holes. This is the valence band, which is where the holes are. We consider the heavy hole valence band, right? And we just call that MP star. Well, NP of E is just going to be equal to negative infinity to EV, valence band edge, GV of E, 1 minus FE, VE, right? And, number of available states in the valence band times the probability of a state in the valence band not being occupied. This is basically what a hole is right here. This is kind of important. A hole is basically the absence, a state in the valence band that used to have an electron that now doesn't. And that's what a hole is. And we get a similar expression for this, which is NV E to the EV minus EF over KT. So that's the number of holes in the valence band for any non-degenerately doped semiconductor. And NV, similarly, is equal to 2